high-speed communication circuits. Today, this discussion will be a prologue, epilogue to the amplifiers, because these circuits that we are going to discuss, they are going to lead towards chips or towards large-scale integration. So the chips or integrated circuits, they contain amplifiers, oscillators, filters, etc. Amplifier is a important component there, therefore we will consider amplifiers. So before going to amplifier, the background, we will make the background required for amplifier. Most of these are well known to you in your college days, or in the first semester you have read devices or semiconductor. So there you are expected to have learned these things. This will be just refreshing the ideas about what you have learned. So again, this lecture is taken from this MIT Open courseware. What we are going to discuss is MOS transistors, passive components, gain bandwidth product for broadband amplifiers, which means amplifier is not narrowband, amplifier is not amplifying at a single frequency, it is amplifying over a range of frequencies. So the range is substantial, therefore it is called broadband. Range is broad, therefore it is a broadband. So in case of a broadband amplifier, we are going to consider the gain bandwidth issues, and the amplifier design uses MOS transistors. Of course, with the transistor is an active device. With that, there will be passive components in the circuit design, therefore the passive components also will consider. And the notes for this you can obtain from the website of MIT Open courseware. I have already given you the website earlier. In this lecture also, the previous slide gave you the website. Now let us come to the large signal behavior of a MOS transistor. I know when you consider a transistor, the behavior of a transistor or the functioning of the transistor, you divide it into two categories. One is small signal transistors, with which you are acquainted in the college days. The amplifiers that you have read in college are mostly small signal amplifiers. Then there is a large signal amplifier. So the large signal behavior that you are expected to have read in the first semester in your devices. Now when we come to large signal behavior of MOS transistor, you know what is MOS? MOS stands for metal oxide semiconductor. So metal oxide and semiconductor. So metal oxide is in the semiconductor. When you design the transistor, there will be metal oxide, and this is MOS transistor is basically a FE. It is not a BJT. So it is a field effect transistor. So if you look at the field effect transistor, then in the field effect transistor, you have a source represented as S, drain represented as D, and gate represented as G. So look at the figures here. There are three conditions in which the transistor can act. The three conditions are: it acts like a transistor or triode, in which when you give the input, then the output is amplified. So you give the input and get an amplified version of the output. Then there is a pinch-off region. In the pinch-off region, if it is operating in the pinch-off region, then the input is not amplified, input is attenuated, it acts like a switch off. The switch is in the off stage. Then there is a saturation region. In the saturation region, it is beyond the active region where the switch is on. So MOS transistor acts either as a switch on-off mode. On-off mode is pinch off or saturation, or as an amplifier, which is it acts like a triode or a transistor. So those three conditions are shown, and the IV characteristics describing this is also shown in the figure. In the figure, if you look at the figure, the x-axis is VDS, y-axis is ID. VDS means voltage between drain and source. ID is the current at the drain. So current at the drain, that increases gradually. So that the portion in which it is increasing, the current in the drain is increasing, that portion is the amplifying portion. Below that is the pinch off region, and above that is the saturation region. All the three regions are shown here. The diode region, which is from radius 0 to delta V, that is up to delta, slightly less than delta V, that core portion. So up to that it is the triode. It is acting like amplifier. Then there is pinch off. Then there is saturation, when even if you increase VDS, the voltage between drain and source, there is not appreciable increase in ID. ID remains almost constant, so it is called saturation. So that is a qualitative example. Now quantitatively, you can find out what is the expression for ID. ID means the current, drain current. Drain current expression is mu n C0x W by L into VGS. VGS is between gate and source, voltage between gate and source, minus VT minus VGS by 2 whole into VDS. For VDS much less than VGS minus VT, if VDS is very small compared to the difference between VGS and VT. What is VT? I hope you know. VT is the voltage due to the temperature at which it is operating. So that expression you may be knowing, exponential k by Tk by I0 into exponential some value something by Kt. So K is the Planck's constant. So that way, and that expression is given Vt. So when VDS is less than, much less than VGS minus VT, then ID is approximately equal to mu n. Mu n is actually the doping that you know, n-type doping. So it is mu n C0x or COX W by L VGS minus VT into VDS, using this approximation. So that is in the triode mode, this expression is valid. In the pinch off region, delta V you can find out as delta V is equal to VGS minus VT. So delta V will be root over of 2 IDL divided by mu n COX into W. I hope you know what is W, what is L. L is the channel length, W is channel width, all those things you know. So delta V is equal to this. Then in the saturation region, ID saturates. So ID is equal to 1 by 2 mu n C0x W by L VGS minus VT whole square into 1 plus lambda VDS. Lambda corresponds to the channel length modulation. How you modulate the channel length. So these are basics of MOS large scale behavior. This is mostly we will use this for design of the MOS transistor, MOS amplifier. Now let us analyze the amplifying behavior of a MOS transistor. In this, the focus will be mostly on small signal behavior, for the small signal behavior, we'll work with a linearized model, so like a hybrid pi model, R model, all those models. So we'll be using a linearized model. You will see the model now. Now to do the small signal analysis, look at this figure. The figure shows you a MOS transistor. Then MOS transistor, the drain is connected with RD, which is RD is the resistor which is connected to the drain to control the current coming to the drain. Similarly, RS is the resistor connected to the source to control the current going out of the source. Then RG is the resistor connected to the gate. It is like your base, emitter and collector. So gate is equivalent to base, emitter is equivalent to source, collector is equivalent to drain. Now in this circuit you can see RD, RG and RS are the biasing resistors. Then biasing voltage is given through the gate, which is V bias, that is the biasing voltage to the gate. Then Vin is the signal which is given between the gate and the ground. Now this Vin will get amplified and will get at the output. Output will be taken between the drain and the source. So that will be taken as VDS. So that is V output. So what we will do here is in the analysis, first we will solve for bias current ID, find out what is the ID. We have seen the expression for ID in the triode mode. So solve for bias current ID, then calculate small signal parameters like again Gm, R0, etc. for the transistor. Then finally we will solve for small signal response using the model that we are using, whether we are using pi model or any other model. Using that model, we will solve for the small signal response of the transistor. Now, let us look at the small signal model for MOS transistor in the DC small signal model. So you can see the transistor here, and you can see the equivalent small signal model here. What we have from the external components are RG, RD and RS. So in the small signal model, which is on the right hand side, you can see RD, RG and RS. Across RS is the voltage Vs. Now on the box, dotted box, that within the box is the model for the transistor. Now for this transistor, and the input is through the gate and source. So VGS is the input. Now VGS, this is the voltage which is controlling the current through the gain of the transistor. Therefore, this transistor contains a current source. Its equivalent is equivalent to a current source which is controlled by VGS. So that current source is VGS into GM. GM is the gain. So VGS into GM is the current source controlled by VGS. Then there is another current source which is because of the VS. VS is this voltage across the source. So that VS into minus GMB. So minus GMB into VS. This is the small signal equivalent circuit. Then the output of the transistor is R0. Through it comes out through R0. So output, in the output we have a resistor R0, small R0. Now what are the expressions for these things? Gm is equal to mu0 C0x into W by L into VGS minus VT into 1 plus lambda VDS. that you can write as root over of 2 mu 0 C0x W by L into ID. Under the assumption lambda ds is much less than 1. If lambda ds is much less than 1, you can neglect lambda ds. So neglect the lambda ds. The rest of the thing you can, from the previous slide, we can put the values of rest of the thing. So we will get it this way. Then GMB. What is GMB in this circuit? Equivalent circuit. GMB is equal to gamma GM. Once you have calculated GM, use that to find out GMB. Gamma GM divided by 2 root over of 2 phi p plus VSB, where gamma is equal to root over of 2q epsilon SNA by COX. In practice, mostly you will use GMB is equal to GM by 5 to GM by 3. Between these two values, these two extreme values, you can take any value. GM by 5 to GM by 3. So lower is GM by 5, upper is GM by 3. Then R0 is equal to 1 by lambda IT. That is the value of R0. Then what are the capacitors which are for the MOS device? In the saturation, when the MOS device is in the saturation, what are the capacitors that we see in the MOS device? Now, see the MOS device, the pictures for MOS device, schematic pictures for the MOS device. From the top, if you look at the MOS device, what you have is, on two sides you have S and D, source and drain. On the left side is source, right side is drain. In between them, there is the gate which is sandwiched. The length of the gate is L. Length of source and length of drain are equal to E. Width of drain and source is W. So L, W and E, now you know what are L, W and E from the top view. Then take a cross section and look from the side. So take a cross section of the amplifier and look from the side. If you take a cross section of the MOS and look from the side, that gives you the side view. In the side view, you can see what are the possible transistor capacitors available in this. So one capacitor is between source and the ground. So source and ground, that capacitor is CJSV. Then one capacitor will be in the junction between source and the gate, that will C0V. One capacitor will be between the junction of the substrate, which is the outside substrate, and the gate, that will be CGC. Then the capacitance between the substrate and the ground, that will be CCV. Then the capacitance between gate and drain, that is C0V. Then drain and ground, that is CJDV. So these are the capacitances available there. Then you can see what is L, length of the gate. Then what is LD, that you can also see. All those things you can see. Now on the source to bulk capacitance, CJSB, expression for that is given here. Similarly, drain to bulk capacitance expression is given here, CJB, JDP, and these are the two side capacitances. Then overall capacitance, COV, that is given here, W LD C0X plus W C fringe. Gate to channel capacitance, CGC is equal to 2 by 3 COX W L minus 2 LD. Finally, channel to bulk capacitance CV, and this can be ignored. Mostly we can ignore the CCV cases. Now, if you look at the device in this saturation, considering these capacitances, the small signal model will now be like this. So what we are doing is we are using the same small signal device model. In that we are just adding the capacitances here. So what are the capacitance that we are adding? CGS, gate to source, CGT, then CGB and CSB. Now if you remember the previous figure, from that figure we know where to add the capacitances. So we add these capacitances. So this gives us the small signal model, complete small signal model considering the capacitances. And now, beyond these capacitances, what will be there in the MOS transistor is the wiring. So different parts we have to wear. Like from the gate, we have to bring out a wire with which we will connect the circuit. Similarly, from the source we have to bring out a wire. From the drain we have to bring out a wire. Now these wires, when you bring out a wire is connected there, so there will be a junction. So those will lead to some parasitics. Parasitic means these junctions, these connections of wires will lead to some generation of some resistances, some inductances and some capacitances. Most effective is actually capacitance. So we'll start with capacitance. So the capacitance will be for the gate, the capacitance from poly to substrate and metal layers. That is where you get the capacitance. Then for drain and source, capacitance from metal through the routing path to substrate and the other metal layers. Now when I say substrate, I hope you understand what is substrate. If you have read in the device, you would have read how a MOS transistor is designed, how to fabricate a MOS transistor. You take a substrate, first you take a substrate layer or a ground layer, over that you put a substrate layer, over that you put P-type or N-type, depending on type of the MOS transistor or depending on type of the FET, you put P-type or N-type on both sides of the substrate. You burn in P-type or N-type into the substrate to form the gate and the source, and above that you have the to burn the drain and the source, and between them you again put a layer of the gate connecting the drain and source. You put the drain, and if it is a MOS, then above the substrate there will be MOS, metal semiconductor oxide will be above the substrate. So that is what a substrate means. Then from where you get the resistance? For the gate, it is polygate has resistance. This is reduced by silicides that we use in the design of or fabrication of MOS. Silicides are used for oxidizing process. Also, these are so polygate has the resistance. The resistance is reduced by silicide. If you put it, this is because of long metal lines. If you use long metal lines, they can add resistance. Similarly, drain and source, some resistance in the diffusion region, in the drain and source, because drain and source are diffused into the substrate. Also, some resistance is there in the diffusion region. This again is reduced by silicide, and it forms the routing along metal lines. Then inductance, again polygate has negligible inductance. Now what is polygate? I am saying polygates most of the time. What is polygate? Polygate is basically the connection of the wire. That is what is polygate. So polygate has negligible inductance, the connection of the wire to the MOS. That is polygate. It has negligible inductance, but long wires can add inductances. So if you are using a long wire for connecting, at the connection point you can have negligible resistance, inductance, but the length of the wire, as you increase the length of the wire, that increases resistance as well as that increases inductance. So long wires can have inductances. Similarly, for drain and source, they become an issue for long wire again. If you use long wires, the drain and source inductances at the drain and source, they become issue. They cannot be neglected. Now, how to get this capacitance, resistance, and inductance? These are extracted. These values are extracted using circuit layout and using. Nowadays, it is easy to extract these things either through experimentation, which is very costly, or through simulations. There are simulation softwares. Using simulation softwares, we can easily extract these parasitic values. Then use these parasitic values there. Then we will consider the frequency performance of a CMOS device. So for CMOS device, two figure of merits will be used, which are common. One is the frequency for which current gain is unit. So you get unit current gain. That is the frequency for which that is one figure of merit. That is called FT. FT is the frequency for which current gain is unit. Then Fmax, it is the frequency for which power gain is unit. So two types of gain we consider. One is gain in current, one is gain in power. If power gain is unit, then it is called Fmax. The frequency at which the power gain is unit is called Fmax. The frequency at which current gain is unit is called Ft. Now, some common intuition about Ft, or the frequency for which current gain is unit. First thing is, for an amplifier, the product of gain and bandwidth is constant. So gain bandwidth product must be conserved. So gain into bandwidth is constant, or gain bandwidth product is conserved. If gain bandwidth product is, which means, what does that mean? It means that if you increase the gain, then the bandwidth will decrease. If you increase the bandwidth, then the gain will decrease. Now here what we are saying is, for Ft, this is the frequency at which gain is constant. Gain is equal to unit 1. Gain is equal to 1. If gain is equal to 1, then gain into bandwidth, this is the frequency at which gain is equal to 1. Therefore, gain into bandwidth, which is constant, gain is equal to 1. So bandwidth will be Ft. So gain into bandwidth is equal to Ft. This is the first intuition. So gain with bandwidth product is conserved because gain with bandwidth product is constant, is conserved, and gain is equal to 1. Current gain is equal to 1. Therefore, gain into bandwidth is equal to Ft. We will also see that MOS devices have an Ft, that is a function of the bias. How you bias the device, that on that Ft depends on that biasing. So this effect strongly impact the high frequency amplification. When you select the topology of amplifier, how to design the amplifier, how to design the biasing circuit, that actually affects what will be the Ft. Now let us look at how people derive Ft for MOS devices when the MOS device is acting in saturation. What we will do is neglect these three components. CDB, you neglect that. CSB, we neglect that. And the second current source, which is minus GMB into Vs, you neglect that. So take out these three outputs. So assumption is that the input is current. We are giving a current as input. Output of the device is shorted. It is short-circuited to a supply voltage, whatever supply voltage you are using. It is short-circuited to that supply voltage. Note that the voltage bias is required at the gate, so we have kept the voltage bias. VGS is there. The calculated value of Ft in the will be a function of this bias voltage. We'll see that later. So this is for the derivation of Ft. These are something that we have to remember. Now using that, we will find out what is ID. ID is the drain current. ID is small ID. Remember, capital ID and small ID are different. Small ID represents the AC, whereas capital ID represents the DC. So capital ID is related to biasing. Small I is related to the function of the transistor. So always remember this in your circuit analysis. When you use the circuit analysis, small I is for AC, capital I is for DC. So ID, this is called to GM into VGS, that is the current source. So ID is equal to GM into VGS, and it is dependent on VGS, which is the biasing voltage. So GM into VGS, that you can write as a GM. Now find out what is VGS. From the circuit you can find out what is VGS. VGS will be 1 by S into CGS plus CGD into IN, whatever is the input current. So input into 1 by S into CGS plus CGD. So looking at the circuit, you can find this out, and from your circuit analysis, network analysis, you know what is this. So from this, what is S? S is equal to J omega. That I hope you know. From the Fourier analysis or Laplace analysis, S comes from Laplace analysis as J omega. Now you can find out the ratio between ID and IN. So ID by IN will be equal to GM by S into CGS plus CGD, and S is equal to J omega, so J omega into CGS plus CGD. So ID by IN is equal to GM by J omega into CGS plus CGD. Okay. Now if you draw a plot between these curves, between this expression ID by IM is equal to GM by J omega into CGS plus CGD. So ID by IM amplitude you take in the y-axis, and on the x-axis you take F. Omega is equal to 2 pi F. So on the x-axis you take F. And when Ft is equal to 1, the value will be F is equal to Ft, that is equal to 1. So if you plot a curve, if you plot a line for which is at F is equal to 1, so that horizontal line corresponds to F is equal to 1. So that plot will cross the slant line at the point Ft. Now Ft will be, if you solve this, that will give us how to solve this. This is equal to 1, which means GM by absolute of GM by CGS plus J omega t into omega t is equal to 1, from which you get omega t is equal to GM by CGS plus CGD. Now from that you can get Ft is equal to GM by 2 pi into CGS plus CGD. And okay, so this is on the derivation or expression for Ft, how to find out Ft. So then we found out the expression for Ft as a GM by 2 pi into CGS plus CGD. Now here you can see there is an expression for GM, CGS, capacitance, One is gain, one is capacitance, the two are capacitances. Then why Ft is a function of voltage bias? Now what are the reasons for that? Reason is Ft is a ratio of Gm to gate capacitances. Now on Gm, Gm is a function of gate bias, while gate capacitance is not a function of gate bias, particularly when there is a strong inversion in the region. So gate capacitance is not a function of gate bias, whereas Gm is a function of gate bias. First order relationship between Gm and gate bias is given as Gm is approximately equal to mu n Cox W by L. We know what are these things, into Vgs minus Vt. So the larger the gate bias, the higher the value of Ft. Because larger the gate bias, larger is the Gm, larger the Gm, larger the value of Ft. So larger the gate bias, larger the value of Ft. Alternatively, Ft is a function of current density. We also saw this, Gm by Cgs plus Cjd. That you can write as approximately equal to root over of 2 mu n Cox W by L Id, that is for Gm. Then for Cgs you can write 2 by 3 WL Cox plus W into COV by W for Cgd. Now this expression is proportional to root over of Id by W. You can see in the numerator there is a root over of Id into W. In the denominator there is W. Therefore this is proportional to root over of Id by W. Then in the numerator there is a root L. In the denominator there is a simple L. In the numerator there is 1 by root L. In the denominator there is simple L. Therefore proportionality is also for L to the power of 3 by 2. So Gm by Cgs plus Cgd is proportional to root over of Id by W into 1 by L to the power 3 by 2. So Ft is maximized at maximum current density. If you increase the current density, from this you can see, if we increase the current density or minimize the L, then we can maximize Ft. Now current density increases by biasing voltage. Now let us come to the second case, unit power gain function frequency Fmax. From the textbook that we have prescribed, look at the textbooks. There you will get this expression for Fmax. You will get the expression as Wmax is approximately equal to 1 by 2 root over of omega t by Rg into Cgd, where Rg is the series parasitic gate resistance. Fmax can be much higher than Ft. This makes the gate resistance small because it is greater than Ft. By proper careful layout of the circuit, when you design the MOS transistor, by properly laying out it, this can be made small. Output capacitance has no effect here. You can also see that this can be tuned out by the inductor. If there is some effect, then that can be nullified by adding an appropriate inductor. As you know, capacitance is minus J by omega C, whereas inductor is j omega L. One is positive, one is negative. Add them together by proper amount, they will cancel each out. So that is, output capacitance has no effect. If there is some effect, that can be adjusted by appropriate inductor. Now comes the speed of NMOS transistors and PMOS transistor, N-type MOS transistor and P-type MOS transistor. What is the speed of them? Now Ft is equal to Gm by 2 pi into Cgs plus Cgd. This is the expression that you should remember. NMOS devices, they have much higher mobility than PMOS devices. That is why you find NMOS devices mostly in all of the ICs, integrated circuits, they mostly use NMOS compared to PMOS. So on the extensive use of NMOS is because of this. NMOS devices have much higher mobility than PMOS devices. In typically bulk CMOS processes, when they are processed, CMOS process is consumed, the CMOS process is adopted, NMOS device will have much higher mobility than PMOS device. Now in this NMOS device, mu n is equal to is approximately 2.5 times mu p. So for many processes, this is the standard. So that implies that Ft for NMOS is approximately equal to 2.5 times Ft for PMOS, because Ft is proportional to mu. So Ft for NMOS will be 2.5 times greater than Ft for PMOS. So NMOS device have much higher, at least 2.5 times higher mobility than PMOS device. NMOS device provide approximately 2.5 times Gm for a given amount of capacitance and gate bias voltage. Also NMOS device provide 2.5 times ID for a given amount of capacitance and gate bias voltage. Now other integrated passive components for RF circuits, we are going to consider them. We will only consider passive components which are appropriate for RF use. RF means radio frequency. So in the radio frequency circuits, the components, the passive components that we are going to use, we are going to consider those things in our discussion. High Q, it should have high Q, low parasitic, and it should have good linearity. Good linearity means the IV characteristics or the characteristics should be linear. So a region operating over the operating region, and this should be linear. So good linearity, these are generally desired things. So bias circuit, except the bias circuit does not look for linearity, at least it does not look for linearity. Bias circuit has no Q. Parasitic are not there in the biasing circuit. Then we will consider about well resistors, diffused resistor. These are two important resistors that we will consider. What is well resistor, what is diffused resistor, that we will come to know later. Well resistors, diffused resistors. Diffused resistors, I think you will know by diffusion, the resistor that is caused because of diffusion. Then poly N plus capacitors, even poly capacitors, they do not perform very well in these regards in terms of high Q, low parasitic, good linearity. Their performance of well resistors, diffused resistors, poly N capacitors, poly capacitors is not very good. Okay. And let us start with this polysilicon resistor that is used in these ICs. Use unsilicated polysilicon to create a resistor. When we design the circuit, we will use unsilicated polysilicon to create the resistor. So the resistor is created using polysilicon, but it is not silicited. So point B and point A, between them we are putting a resistor. So it is polysilicon, so therefore the resistance is R. Because of polysilicon, you are putting a polysilicon, and In practice, that is the schematic AB. On the left hand side, we see the point AB, with in between them there is a resistor. That is the schematic. In practice, how do you lay out it? You take the point A to the point B, join a line which is muon dot. So from A you move towards right, then go downward, then move towards left, go downward, move towards right, go downward, move towards left. What is the advantage of this way? This way, if you design it, the advantage is A to B length is small. Now using this, you are increasing the length. Using this type of thing, within the small distance, the length is actually increased. Now length is increased, accordingly you increase the or you vary the resistance. So according to your resistance, you choose the length. According to the length, you design this method. So this is the layout. In the layout, you put polysilicon. Okay, along this layout, put the polysilicon. Now what are the key parameters here in this design? One is resistance, that is the important part because we are considering resistor. So our resistance is the key parameter. It is about 100 to 200 ohms per square. Okay. Then parasitic capacitances, because we have two lines, so between them there will be parasitic capacitances. Usually small, they can be neglected. If you have, these are appropriate for high speed amplification, this parasitic capacitances. Then linearity is excellent here. Accuracy will be within plus minus 50%. So these are the key parameters if you design a polysilicon resistor. Now instead of a polysilicon, you can also use a MOS device. So a MOS resistor. You can have a MOS resistor instead of a polysilicon. So use a MOS instead of a polysilicon, or instead for the resistor, use a MOS. If you use a MOS here, we write it as RDS. The resistance is RDS between drain and source. The resistance comes between drain and source. So you can see how it is to be connected. So gate is grounded, source and drain, they are connected as a resistor. Okay. In this case, RDS expression is given here. RDS is approximately equal to 1 by mu COX W by L VGS minus VT minus VDS. High resistance value can be achieved here in terms of mega ohms with tens of square microns. Small size and mega ohm resistance you can achieve here. In the previous case, it was in ohms. Here it is mega ohm. So small resistance, you use polysilicon. High resistance, we use MOS resistors. Parasitic capacitance is large. Because of gate capacitance, you will have large capacity capacitance. Resistance is quite nonlinear. This is appropriate for small swing circuits or DC bias circuit. There you require nonlinear resistance. For biasing, DC biasing, you require nonlinearity in resistance. So this resistor is suitable for DC biasing circuit, or if you have a high swing circuit because of nonlinearity. So with this, let us take a break here, lunch break. After lunch, we will discuss what is remaining. So we will be discussing at 2:30. Come back at 2:30. We will discuss other parts, other components, and gain bandwidth product. That we will discuss at 2:30. Let us take a break here. बंद कहीं कर दो